The following diagram represents a hypothetical reaction, A turning into B, with A represented by the red spheres, B represented by the blue spheres. The sequence from left to right represents the system as time passes. Do the diagrams indicate that the system reaches an equilibrium state? Explain. Chemical kinetics was all about what was going on with the reaction before the reaction stopped. You know, how fast were the concentrations of the reactants changing into products? How fast were products appearing? Equilibrium is all about when the reaction stops. What are we left with? How much heat was released? How much heat was absorbed? What's the concentration of the reactants when the reaction stops? Now, the thing you have to understand with most of chemistry is that reactions are reversible. So in our hypothetical situation here, as the red balls turn to blue balls, the blue balls start turning back into the red ones, and so on until a set concentration occurs. And the rate of the blue ones turning back into the red ones and the red ones going forwards and turning the blue ones stays constant. So looking at these diagrams, I'm looking at the last two, the amount of red balls to blue balls isn't changing anymore. So yeah, this reaction has stopped and we're at a state of equilibrium. So when the concentrations stop changing, the visualization is that the forward rate of reaction is equal to the reverse rate of reaction, and the reaction's over. So yes, we're at equilibrium. The following diagram represents an equilibrium mixture produced for the reaction of the type A reacting with X to form AX. If the volume is 1 liter, is K greater or smaller than 1? All right, this is an important number. Is the K value greater or smaller than 1? If it's smaller than 1, it means that when the reaction stops, I'm going to have more reactants left over than products made. If it's greater than 1, it means when the reaction stops, I'm going to have more products than reactants when the reaction stops. So when I count up what's left, A represented by the red ones, X represented by the blue ones. I've got 3 red ones, 2 blue ones, and I've got 8 of the AX combination. So since there's a higher combination of AX at the end of this thing, this reaction is said to be product favored. Meaning when the reaction stops, I got a lot of products and less reactants left over. A K value greater than 1. A friend says the faster the reaction, the larger the equilibrium constant. Is your friend correct? Why or why not? Your friend is incorrect. Speed of reaction has nothing to do with the position of equilibrium. There are very spontaneous reactions, meaning I make a lot of products, lose a lot of reactants that occur quickly, just as there are a lot of chemical reactions that are spontaneous that react very slowly. So speed of reaction has nothing to do with what the position of equilibrium is going to be when the reaction stops. The diagram shown here represents the equilibrium state for molecule A reacting with 2 moles of B to make 2 moles of AB. Assuming the volume is 2 liters, calculate the equilibrium constant Kc for the reaction. All right, so looking at my container there, I've got 2 red molecules and 2 blue ones just sitting there, and I've made 4 AB ones. They told me that the volume was 2 liters, so 2 moles of each gas is represented by the spheres, divided by 2 liters, it gives me the molarity of A and B. 4 moles divided by 2 liters, it gives me the molarity of AB at equilibrium. All right, so to know what the magnitude of the equilibrium constant is, I have to plug into what's called the law of mass action. The law of mass action is defined as products over reactants raise the concentration of the products over the reactants raise their stoichiometric coefficients. So the brackets represent moles per liter. So if I have A amount of A reacting with B amount of B, I take moles per liter of A at equilibrium, raise it to the A power, moles per liter of B raised to the B power, and divide it into the concentration of C raised to the C power times the concentration of D raised to the D power, and that'll give me whether this reaction is spontaneous or not, whether I have a K value greater than 1 or not. So products over reactants raise their stoichiometric coefficients. So I take the concentration of the products, AB, which is 2 molar, and raise it to the second power because I have the coefficient for AB is 2. I take the concentration of A and raise it to the first power and multiply by the concentration of B raised to the second power and divide it into the concentration of the products. And I get a K value with a magnitude of 4. B. If the volume of the equilibrium mixture is decreased, will the number of AB molecules increase or decrease? All right, when you have an equilibrium involving gases and you put it under pressure, and that's what we're doing when we decrease the volume, the system responds by driving to the side with less moles of gas. So according to the coefficients, I have, for every 1 mole of A, I have 2 moles of B going into this reaction. So I have 3 moles of gas going in and 2 moles of AB coming out. So this is a gas-reducing reaction. 3 moles of gas going in, 2 moles of gas coming out. So if I pressurize the system responds to try to get rid of that pressure, drives to the side with less moles of gas. So I'll be making more AB if I put this system under pressure. I'll shift that equilibrium toward the AB side. In number 15, write the Kc for the following reactions. In each case, indicate whether the reaction is homogeneous or heterogeneous. Kc just refers to an equilibrium constant where you're using concentration units, moles per liter. When we're writing the law of mass action, anything in the gas phase or the aqueous phase gets put into the law of mass action. So for A, 3 moles of nitrogen monoxide in the gas phase, making 1 mole of dinitrogen oxide in the gas phase and 1 mole of nitrogen dioxide in the gas phase. I put the concentration of the products over the concentration of the reactants, raise their stoichiometric coefficients. And the brackets represent moles per liter. So this would be the law of mass action for this reaction. B, methane in the gas phase. Dihydrogen sulfide in the gas phase, carbon disulfide in the gas phase, and hydrogen in the gas phase. Everything's in the gas phase. Everything's going to appear in this equilibrium expression. So I take the concentration of the products, raise it to their stoichiometric coefficients, and divide it by the concentration of the reactants, raise their stoichiometric coefficients. So that's A and B. These are both homogeneous equilibria. All right. The only way you get to be a heterogeneous equilibrium is if you got a solid. So looking at C, I see our first solid. So we have a gas becoming nickel solid and 4 moles of carbon monoxide. All right, so solids don't appear in equilibrium expressions. So if you've got a heterogeneous equilibria, you leave the solids out of the equilibrium expression. So this equilibrium expression is just the carbon monoxide concentration raised to the 4th power, divided by the reactant concentration raised to the 1st power. D, back to homogeneous equilibria, right? Everything is in the aqueous phase, so everything appears in the equilibrium expression. If we're looking at E, we've got solid tin reacting with zinc in the aqueous phase, making silver in the aqueous phase, and zinc in the solid phase. So again, solids don't appear in the equilibrium expression. They have no effect on the position of equilibria. So it's all about the concentration of the reactants in the aqueous phase or the gas phase. Oh, I can see I left aqueous out of with that zinc 2+. Aqueous phase appears in the equilibrium expression, not solids. Liquids either All right, so when we're talking about the autoionization of water, right? Water breaking apart to form H plus ion hydroxide. Liquids don't appear in the equilibrium expression. This is an aqueous environment, and the amount of water you're losing here is inconsequential to the amount of water you have. So equilibrium is strictly governed by the concentration of the products, raise their stoichiometric coefficients, divided by nothing. All right, there's nothing that appears in the denominator here. G, interesting, right? So we're balancing the equation differently, right? 2 moles of water making 2 moles of H plus ion, 2 moles of hydroxide. We're not in lowest whole number coefficients, so this would be balanced wrong if we were balancing earlier in the course. Nonetheless, if you write the equilibrium expression this way, it has an effect on the equilibrium constant. So you raise the concentration of the H plus ion and the hydroxide to the second power. It has an effect on the magnitude of Kc. So equilibrium expressions are sensitive to how you balance them. 22. Calculate Kc at 303 Kelvin for SO2 reacting with Cl2 to make SO2Cl2 if the Kp value is 34.5 at this temperature. All right, so Kc is an equilibrium constant where we're solving using concentration units, moles per liter, because pressures can appear in equilibrium expressions. Now, you can talk about pressures in terms of their concentration, moles per liter, but we can also talk about them in terms of pressure units. So you can solve for Kp using pressure units or moles per liter, but you're going to get a different value. So there's a relationship between the two. You can convert between a Kp value and a Kc value by multiplying it by RT, the gas constant, temperature in Kelvin, raised to the delta N. So in this problem, they gave me Kp. So if I divide both sides by RT raised to the delta N, I can solve for Kc by plugging into this. The trick here is, what is delta N? Delta N is defined as the sum of the coefficients of the gaseous products minus the sum of the coefficients of the gaseous reactants. So looking at this equation, I've got 1 mole of gas reacting with 1 mole of gas to make 1 mole of gas. So the sum of the products is 1. The sum of the reactants is 2. So if I subtract 2 from 1, I get a delta N value of -1. That means I raise RT to the -1. I really shouldn't have put atmospheres in there. When you're talking about a Kp value, it's unitless. There isn't a unit, so atmospheres really shouldn't be in there. And so Kc and Kp are unitless. As that's different than with kinetics, right, where the rate constants had a unit. Equilibrium constants don't have a unit. So when I divide RT raised to the -1 power into Kp, I solve for Kc. So they both represent a spontaneous reaction, but they're a different value, right, because they were calculated using a different unit.